YouTube, this is my third video that I'm doing on my module on the trig identities, and this is most likely the most intensive one, but it is over what we call the Pythagorean identities, okay? So we're going to get right to it. As a matter of fact, the first thing I want to do, though, is kind of make one note. We talk about notation. So I say, recall that in trig, when we write sine squared theta, or like cosine squared theta, maybe tangent cubed theta, in this instance, sine squared theta would mean the same thing as sine of theta squared. So that means we have to find the sine of that angle first, and then we're going to square it. So before we kind of start in with the Pythagorean identities, I just kind of want to work through these couple of examples real quick. But we said, what if we assume for the first one here, sine of theta equals 3/5? I want to go find sine squared of theta. Okay, so just to be clear on this one, when we say sine squared of theta, we mean the same thing as, and we typically don't rewrite it this way, sine of theta squared. And in this case, we know that theta is 3/5, so we could just substitute this in, and we get 9/25 would be the solution there. The next one I say, let's go find cosine cubed of theta. And in this instance, you see here, I say, well, in the second one, cosine of theta is -1/2. So instead of actually rewriting this the long way, we could just say, let's go ahead and do this now. We say, I realize that this means -1/2, which is the cosine of that number, then we'll cube it. And if we cube the top and the bottom, of course, -1 cubed is -1, and the bottom there, 2 cubed is 8, so -1/8. Okay, so just want to be clear on the notation. So let's go ahead and get started with our Pythagorean identities, which, by the way, we have to borrow from our definition of the trig functions in order to derive these. Okay, so we're going to find out how do we get these Pythagoreans in the first place. Recall that if we had an angle in standard position here, we say, and a point on its terminal side, xy, then we would have the following thing. So I'll kind of sketch this in really quickly here. But if we had some angle in standard position, recall standard position just means that its initial side leaves the positive x-axis. There's our angle, theta. And we know a point xy on the terminal side. So we'll call this the point x comma y. And we'd say we'd have this right triangle-y thing where it has y in its height, x in its width, and we'll call this distance back from the point xy to the origin, we'll call this distance r, where r is always positive. But we could derive these. We say, well, then sine of theta, which would be the opposite over hypotenuse, that would be y over r, and that's what we have listed here. And we say cosine of theta, that would be adjacent over hypotenuse with our angle theta here, that'd be x over r. And of course, tangent, which we learned in the last video is really just sine over cosine, but it would be opposite over adjacent, which is y over x. But using this, now we are going to derive these trig formulas, or the trig form of the Pythagorean. So let's start with this. Pythagorean, we say, is x squared plus y squared equals r squared. If I go too fast in this video, just go ahead and pause it and rewind it. But we say, well, the first thing we're going to do is, we're going to just, for the sake of, playing around with this, we're going to divide both sides by r squared. Everything by r squared. And what you'll notice is this, the right side becomes 1. And on the left side, we end up with this. We say x squared over r, let's undo this here, r squared plus y squared over r squared is 1. It's important that it equals 1. But moving from here, we'd say, just using algebra, we know that if we were to take x over r and square it, we'd get the same thing as x squared over r squared. So this is really just the fraction x rths squared plus y rths squared equals 1. But from above, now we're going to borrow from our trig here. We say, well, sine of theta is the same thing as y over r. And cosine of theta is the same as x over r from our definition over here on the left. So everywhere I see an x over r, let's just write this instead. We say cosine of theta. That's what's being squared here. Plus the sine of theta, which is y over r. That was what was being squared there. And then using proper notation, we could just say this is cosine squared of an angle plus the sine squared of that very same angle. This must always equal 1. Put this in your brain. This is always true. But we say for any angle, cosine squared plus sine squared is 1. And so remember, with identities, means the left side is always equal to the right side. So if I were to ever see, say, for example, cosine squared plus sine squared, if I were to see this on paper, I could write down 1 in its stead and mean the exact same thing. Okay, so this is not the only form of the the trigonometric Pythagorean identity, but this is certainly the primary Pythagorean identity. Okay, what I want us to realize is when we look at the Pythagorean identity, what it's doing is it's really relating kind of sine and cosine. As a matter of fact, let's say if I I know cosine, we could plug it in right now for this cosine squared, and work backwards to find sine. And likewise, if I know here sine of theta, we could plug that in and go back and find cosine. The thing here is this. The Pythagorean identity is a very nifty way to see either sine or cosine and then go find the other one. And so if that is the case, actually what we'll do is we'll rewrite this in terms of just cosine or just sine. If that's the case, let's say I already knew sine. I already know sine. I want to go find cosine. Before plugging that in, let's just go ahead and isolate. Let's isolate the cosine, which means let's get this by itself. So we could subtract sine squared from both sides, minus sine squared of theta, gone. So we get cosine squared of this angle would be equal to 1 minus the sine squared. This is also always true. And then also to isolate this, we want to get rid of the squared. We'll take the square root of both sides, square root. And so we get this. Finally, the cosine of the angle theta from our Pythagorean identity is always plus or minus the square root of 1 minus the sine of the theta squared. Okay, so we say this is one alternate form of the exact same identity down here, but the nice thing about this form is this. It says, here's how you find cosine if you already know sine. You can just plug it into this square root over here and you would have cosine. Okay, so the one thing I want to point out here is this, the plus or minus in front. It does not stay plus or minus. It actually will have a definite answer, but it depends upon what quadrant theta terminates in. Okay, so from this, real quick, I just want to bring up one more kind of solid fact. These are not the only Pythagorean identities. We have, let me get rid of that, and we'll go in order here and in blue. We had cosine squared theta plus sine squared theta to begin with. This was equal to 1. If we were to divide everything, just on a whim again here, divide everything by, say, cosine squared of theta. Why not? Cosine squared of theta. Cosine squared of theta. What I want us to recognize is really this. Cosine divided by cosine would become just 1. And we know this, sine squared over cosine squared, this actually becomes sine over cosine from our ratio identity. We know that sine over cosine is tangent. So sine squared over cosine squared is tangent squared. And we say, well, this right here, this is just the reciprocal of cosine. What's the reciprocal of cosine? That is secant of theta. So again, this was not the only alternate form. There's another alternate form of the primary Pythagorean identity. We could have divided through by sine squares, but the nice thing about this is it relates tangent to secant. So again, if we knew, say, tangent, we could plug it in and we could go find secant. So all this being said, let's go ahead and put this into practice here. But the Pythagorean identities, they are all listed here. And you'll notice these equivalent forms, man, I would memorize those. That cosine of an angle is always plus or minus the square root of 1 minus sine squared, and vice versa with sine. And also you'll notice that here's that first form we just derived, 1 plus tangent squared of an angle is always the secant squared of the angle, but if we had divided through by sine squares, we would have gotten 1 plus cotangent squared theta equals cosecant squared theta. So one thing, or a couple things I want to point out are these. First of all, these are nifty if we ever want to rewrite an expression using a more convenient form. So for example, perfect example, if I ever saw cosine squared plus sine squared of an angle on my paper, I would so totally erase it and just write 1, because it means the same thing anyways, and 1 is so much simpler to write. And the second thing these are nifty for is if we wanted to find a trig function in the equation when the other one's already known. So like in the first identity up here, I say I could find cosine if I knew sine, or if I knew cosine, I could plug it in right here in this formula and go back and find sine right here. So this is exactly what I'd like to do with this example up here on the right, and we'll be done with this video. So let's say we know that the sine of theta is 3 over 5 and theta stops in the second quadrant. And what we want to do is find both cosine and then move on and find tangent theta while we're at it, okay? So here's the deal. I know sine, I want to find cosine. So looking back over here on the left, these things that I'm going to memorize, okay? I notice that the equations that equate or relate cosine to sine are over here on the right. And if I'm finding cosine, then what I'm going to do is I'm going to use this one right here, which says, hey, cosine would be equal to. As a matter of fact, cosine equals plus or minus the square root of 1 minus sine of that same angle squared. But the good news is, recall, we know the sine of this angle. So we say 1 minus the square of the sine of this angle. We'll just plug in that 3/5. So now a few things we need to say about this as we simplify it. Cosine of theta is still plus or minus the radical of something. But when you square a fraction, you square the top and the bottom. So instead we'll have 9/25 as we kind of had on the front. And the other thing is this. You're going to need a common denominator in here. And since you're always in these formulas and these identities, subtracting this fraction part right here from 1, your common denominator is always just going to be whatever the denominator of this one is. So we might as well call this 25/25, which is 1 whole, minus 9 of those 25ths. And this leaves behind cosine of theta equaling plus or minus the square root of 16/25. And I won't do this in every video, but I just want to point out, just like when you square a fraction, you square the top and the bottom. When you square root a fraction, you're taking the square root of the top and the square root of the bottom. So we end up with cosine of theta, finally, equaling plus or minus radical 4/5. Now, one thing I want to point out is this. Only one of these is right. So we have to find out, well, which one of these would be the accurate one, the positive or the negative? And the key lies in this. We knew that theta terminated in quadrant 2, okay? So we say theta is some angle that terminates over here in quadrant 2. So using what we know about the trig functions, we say, if you've seen this mnemonic, all students take calculus. Come in. So we say all students take calculus. Sorry, somebody's knocking on the door here. We can look at this S right here. We say that sine is the only positive one that is positive in the second quadrant. So if sine is the only trig function that's positive in the second quadrant, then cosine is negative. Everything else is negative in the second quadrant. So we could say of these two, we'll actually cross them out and we'll keep the negative one. So we'd say in this instance, we get negative 4/5. And that is how the Pythagorean identities are derived and how they work for us.